Okay, we start up. Today's topic will be elliptical equations. You haven't really started on that one in the lecture yet, but I think you will get it already now on Friday. What is an elliptical equation? Well, that is where we have problem solving it. That's where we pay the price in CPU. So we start with the simplest possible elliptic equation. Say the double derivative with respect to space equals to 0. From fluid mechanics, you should remember that one, or recall that one. Double derivative of the velocity is 0. Okay, then you will have a linear velocity profile. For instance, now you want to solve, say, a cuvette flow problem. You have a steady wall down here. Up here you'll have, say, 1 meters per second velocity of the wall. What is the solution? Well, laminar flow, you will have a straight line velocity profile given by that equation. So fairly easy to integrate it twice. You'll have two integration constants. You need two boundary conditions, which you have, so not a problem. Solve that one numerically. Okay, in elliptical equations, you are going to need boundary conditions all around your boundary. You have to specify him, or the derivative of him, all around. In a one-dimensional problem, it will mean here and here. Very simple, of course. So not a problem there. But in a 2D, 3D, you need boundary conditions all around. So here you don't have any possibility to marching the solution forward in time, or space for that matter. You don't have an open boundary. That's not possible. So the sad thing then is any solution at any point actually depends on all the other ones. So it's very coupled, you might say. Let's solve this one numerically. So we approximate him with ui plus 1, ui plus ui minus 1 divided by delta x squared. So that's central space scheme, second order accurate. Now, very convenient for me, I had chosen the Laplace equation. So double derivative equal to 0. Okay, then I can just skip him. And we should have our very, very simple first solution. Well, I just rewrite the entire equation system, don't I? To say that ui equals, just isolate him. Well, it will be something like 1/2 ui plus 1 plus ui minus 1. So he should be sort of the average value between his two neighbors. Yeah, well, if you knew the neighbors, the problem is solved. Of course, you don't know the neighbors, so we are talking here, of course, about an iterative process. So I'll use that one as an iterative scheme. Very stupid, very silly for a one-dimensional case. Of course, you would have solved this one by hand. Numerically, you would have used a direct method. Coming back to that. But now I will sort of do it the worst possible crude way. But it's a very simple way. So let us put up some number of unknowns. We have to define our grid system here. So I start here with number 1. That's the boundary point. And up here, well, I want to have Emax unknowns in between. So then this guy up here has to be Emax plus 2. So the first one and the last one, they are the boundary values here, constant, 0 and 1. But the rest in between, I want Emax And Emax, well, let's take 100 points. Remove the light, like that. Emax is 100. Then we are going to need the vector u, which then has to be fairly big. Zeros of Emax plus 2, but it's a one-dimensional case, so it's only comma 1. Now we can use the boundary condition immediately. First one should be 0. Well, he's already there. Everything is 0 initially. So now I can write u of Emax plus 2. I'll put him to be the boundary value. Like that. And then, well, we should be able to make a plot. That should be our initial field. Let's see if he runs. Yeah, so far so good. You start with everything equal to 0, and the last point, 102. There you have the jump. So this is the initial velocity field. Velocity now going upwards. Then we start using our dummy scheme. So what should we write here? For iterations, iter equal 1 to, I have no idea, say 100. Now for every iteration, we now have to go through all the internal points and then update them according to this recipe. So that should read something like for I equal 2 all the way up to Emax plus 1 only. There we have it. And then I just write the formula. U of I equals the sum of u I plus 1 plus u of I minus 1 divided by 2. There we have it. Now we have swept over the internal domain once. So that's one iteration. And then we should make another plot. Plot u. And I tell him to do it now, or else he won't do it. And end. So let's put in a pause up here so that I can fit the window. Let's see if this one works. So that's the initial state, everything equal to 0, and singularity up there. Yeah, well, he's getting there. The solution, the correct solution, should be a straight line. So he's just in the beginning. We are going to need more iterations here. So let's try 1000. He's getting there. And yes, actually this method will work. But you see, he's very slow. That was 1000 iterations. And if you have many unknowns here, I just had 100. If I go to, say, 1000, he will take even longer. And you go to 10,000 or whatever. This is a very, very slow method of solving the equation system. Possible, but very, very, very slow. So let's go back to 100 here. How can we speed things up? How can we make it faster? Well, we have some options, of course. That one was not so smart. We could introduce time. I don't have time, but it shouldn't be illegal, should it? So instead of the elliptical equation here, I write it on the form time derivative equals double derivative with respect to space. And then I just seek the steady state solution. That is actually an easy option. If you have a very complex elliptic equation, you can't really solve it. Well, you can always put the time derivative in front of it. That's not illegal. And just say, okay, I want to solve this one, and then I just let time go to infinity, finding the steady state solution if it exists. So this one would actually be sort of an obvious way to solve it. How would that one be solved? Well, I use forward time, central space scheme, straightforward. So then you will have ui, new time level, minus the old one, over delta t equals, and then on the other side, ui plus 1, ui plus ui minus 1, divided by delta x square, and then everything at the old time level, like that. And rewrite that one. Then you will have it on the form ui n plus 1 nu equals, and then you throw everything else on the other side. So you have the center point here and here. ui n should now be multiplied with 1, and then you will have minus delta t up here, so it will be something like 2 times delta t over delta x square, something like that. Then we have the two others, I plus 1, I minus 1. Well, both of them will be multiplied with delta t over delta x square, and then you'll have ui plus 1, ui minus 1, level n, something like that. That should be the FTCS scheme. But if we are going to do it like this, we run into stability problems. Of course we do. If you can recall the 1D diffusion equation. If you take the quick and dirty stability analysis here, if you add all the coefficients for all these unknowns, here you have 1 minus 2 something. Here you have 2 times the same something. So the sum of the coefficient is 1. Okay. Then you can use this crude method by saying if all the coefficients are positive, then you are dead certain that this is going to be stable. Meaning this guy, he has to be positive, meaning delta t has to be smaller than something. So that will be our limitation if we do it like this. And yes, we could do it, but it turned out that it will be actually more or less the same as what I've done here. So this is also going to take forever, sadly. We could use an implicit method, but that's the same as solving everything with a direct method. It's sort of cheating. So what else then can we do? Well, first of all, if you look at the recipe that I programmed, a very simple one, versus the one I should have used if I had time. There's something wrong here, isn't it? Here I have the new one based on not just old values. One of these is going to be freshly updated from the previous I number. So here's a mix. One of them is from the previous iteration, but the other has just been updated. So I have actually programmed it wrong. What I should have done, according to this way of thinking, would be something like this. I have to create a new solution here. Then To make this one more correct, I should then up here write new u equals the old one, then just duplicated it. And then after finding all the new ones based on just the previous values, then I can update everything in one swoop by writing here u equals new u. Now I only use old values. So let's try to run that one instead and see if it helps. And no, it doesn't help. Actually, it has become slower. So this way of programming, using only the old values all the time, this one is called a Jacobi iteration. Jacobi, only old values. And it's not a smart idea to doing it like this and then removing this one. Now it is called Gauss-Seidel iteration. Jacobi, Gauss-Seidel. Gauss-Seidel, he uses the freshly updated values as soon as they are available. That's okay. And he's actually a little bit faster than Jacobi. Not much. They are of the same family. So still not a good solution. But you should know the difference between those two. And Jacobi, that is the way you would have programmed it if you had used time. You see on the right hand side here, everything is from the previous time step instead of a mix. Okay, how else can we write or solve this equation system? Forget about the time solution. As I said, it won't be faster. It's not worth the effort. If we do something like this instead, invent a function. And the function, that is your stencil written on the form equal to 0. So my stencil here reads something like this. ui plus 1, 2 times center point, plus ui minus 1. Then, of course, equal to 0. If this one is 0 for all different possible values over the index I, you have found a solution. So I want this f function to be 0 all over the place. How to find a 0 for a function? Well, you have something called a Newton-Raphson iteration procedure. So say here you have your function f with respect to something, for instance x. Find the x that gives my function, that makes my function become 0. How do you do it? You start by guessing, wild guess. Here, this is my first guess, x1. Okay, then you go up here and you get something that was not 0. Okay, then you know, first of all, you guessed wrong. But you use now the arrow, the difference from 0, to adjust the new x. And how can we do that? Well, Newton then found out that if you create the derivative, find the derivative at this point, and then you prolong it until you hit the x-axis, then you use this one as the second guess. Very, very smart. And so you can continue finding this point fairly rapid. So the Newton-Raphson reads something like this. The new f, no, sorry, not the new f, the new x, of course. The new x equals the old one minus your function divided by the gradient derivative of fi with respect to the point that we have sort of picked out. What will our f function here be? Well, it is this one. What's the derivative? Well, I'm focusing on the center point ui, so the derivative is -2. That's all. Okay, so according to this recipe, we have the following formula. I can use n plus 1, but not meaning time. N superscript now means iteration number. So the new value equals the old one from iteration number n. Then we had minus will become plus, and then we have the entire function. That is ui plus 1, ui plus ui minus 1 divided by 2. That is our recipe. And if you continue, well, leave it for now. Yes, this method actually works, but if you can look at the calculation here, what do we actually get? I have ui minus 1/2 here, minus ui, so he disappears, and I'm left with ui plus 1, ui minus 1, 1/2, which is exactly what I started with. So far, not helpful at all. That was too bad. Then we do the smart thing. To find the 0 point as fast as possible, it is then shown that if you use this adjustment here, you can think of it as finding a better guess. You take the old one and then you have some adjustments. If you take this adjustment and then you overdo it, you multiply with a parameter there, and then maybe he is 1.5 or 2 or 3. You sort of overdo the adjustments. Then hopefully we should reach this point faster. Shouldn't have to use that many iterations. So that will mean we have to take this parenthesis here, the f function, and then multiply with an omega. So what will my recipe be now? Well, I have ui n multiplied with 1, and then I have minus divided by 2. It will be 1 minus omega, like that. For the other two, you will have an omega multiplied with them and then divided by 2. So they should read something like this. Omega ui plus 1, ui minus 1, and then divided by 2. So now you see omega equals 1. You are back to what we started with. But now at least we have another parameter we can play around with. Let's see if that one helps. So omega equals, we can start with 1, just to be sure that we get the same answer. Then I will rewrite this one to be an fi instead. I'll write it on this form. So fi then should be equal whatever we had here, Control X there, and then also minus 2 times the center point. So this is my f function, like that. And if he is 0, then, well, I have the solution. So now I could use him as sort of a residual If I sum up all of them, say absolute value, then I get sort of an idea, have I solved all my equations or not? So if I write a residual here equal to 0, and then down here I write residual equals residual plus absolute value of Fi. Then I can use this accumulated residual to see how well have I solved my equation system. Okay, now back to the recipe. Then we write it on the form u of I equals, and then we had the old one, u of I should be multiplied with 1 minus omega. And then we had plus omega multiplied with, then we had the sum of these two guys, like that, divided by 2. There we have it. So this now with omega 1 should be exactly the same as I had. Any questions so far? That's okay. We can even print out the residual, can't we? Title. What should we write here? We should write something like residual equal numerical to string the rest. A couple of digits. Let's see if this one works. Yeah, well, he works, but you see the residual is decreasing very slowly. So yeah, he will find a solution in the end, but it's going to take forever. Yeah, before we start playing around with omega, remember here, I don't have a time development. And I started here saying my internal field was 0. Of course, that's just an initial guess. Stupid, bad, but I mean, you have to put something. Let's try to put something else. Say for the internal field, u from number 2 all the way up to E max plus 1 equals something else. We could try with 0.5. Then we have this initial situation. Yeah, actually maybe a little bit smarter. Oh yeah. So having a good initial solution, maybe not so bad. Definitely a smaller residual, 0.003. If you have no idea what your initial state should be, or initial guessed solution, you have something to play around with here, random numbers. MATLAB has a random generator, numbers between 0 and 1. So then my initial field now looks something like this. Total rubbish. Let's see how this one, if that one helps. Yeah, actually, it at least faster than 0. Almost the same as guessing 0.5. So using random, that might not be such a bad idea, depending on the problem, of course. Yeah, but we roughly get the same end residual, 0.003. Now, let's try playing around with omega. I remove this one, so we are back to the 0 initial field. Let's try with omega equal to 2. Omega equals 2. That looked very strange. Now what's he doing? Omega equal to 2. Let's crash him. What is he then doing? Omega equal to 2. Well, then you'll have the sum of these two minus this one. So he's sort of just flipping the solution here. So omega 2, that was not a good idea. Omega 3, what about that one? Omega 3. No, that was definitely not a good idea. He explodes. So you can play around with different omegas, and you will find out that omega has to be between 1 and 2 for a good performance. So 1.5. Faster, but still not that fast actually. And it turns out when you start playing around with omegas, if you have many unknowns, here I have 100, if you have many of them, he should be quite close to 2. So here a good omega should be something like very close to 2. Let's try 199 just to see what happens. You see, you sort of overdo the adjustments. So maybe 199 was a little bit too much. But still, definitely much more efficient all of a sudden. So it's a very simple method, and it works. So just using this one, adjusting with the omega, very, very good idea. Now, have a peek of the two versions that we now have here. This was with the FTCS scheme, very slow. This is what we have with the what is called a modified Newton-Raphson, or a successive over-relaxation when you have an omega bigger than 1. They are sort of actually the same, on the same form. You have here 1 minus omega. So if you baptize this one as an omega, then here you then have omega half, which is exactly what you have here. So the recipe is actually exactly the same. We just call this one for omega, and then we should be good to go. But here we were not allowed to have this parenthesis negative. Then he explodes. Here, using an omega bigger than 1, he's negative. But that's okay. So what's happening here? Why can't we do it here? We immediately run into problems with the diffusion equation when we had a too big delta T. Why don't we have the same problem here? Anybody see the reason? Question 1A on the exam, of course. That one is not easy to see. But remember, look how I programmed it. I programmed it with the philosophy of Gauss-Seidel. Use the updated value as soon as you have them. So I don't have a new U here. I have a mix on this side. One of these is going to be from the previous iteration. The other one has just been updated. I'll show you. If we now go back to the Jacobi scheme, then we do it like this. You don't overwrite. You demand that in the calculation everything should be from the previous iteration. Okay. Then, of course, after you have swept across the entire field, you have to update him. So now let's try that one. and he explodes. And actually, if you now choose an omega just a little bit above 1, he explodes. So now you are, with Jacobi, you are in the same problem as we were with the diffusion equation. You can't violate the stability criteria. Then you have to use a different scheme. First order, well, not upwind here, but you could use an implicit scheme or something. So no, you can't use Jacobi iteration when you want to use an omega bigger than 1. You have to use the Gauss-Seidel iteration. Something like that. I don't remember the optimum. What did I find here? No, it's not listed even. So you can sort of play around with these omegas to find the best one. That one looked very good, actually. There are some numerical theory how to find the optimum omega, to find the smartest one. And you can do it for such simple equations. You can find an analytical expression for it. For more complex problems, you can actually spend more CPU finding the optimum omega than just to solve the problem. So for an engineer, you don't care. You just try with different numbers, and you will quite rapidly find a fairly decent one. Just keep in the back of your head, many unknowns, big omega. But it's also depending on the boundary conditions, if you have derivative equal to 0, stuff like that. Okay. Any questions so far? How would you solve this problem directly? So now we have a fairly good solution, a fairly good omega. Let's stop him after only 10 iterations. 10 was a little bit too few. Give him 100 then. Yeah, okay. We are on the way, but we haven't solved it. How would you solve this equation system directly, with a direct method? I assume you have gone through the backslash? No? Okay. We can do it quite rapidly. Let us remove all the stupid things we did up here. This is your equation system, and everything equal to 0, so you can just multiply by delta x squared, and then he's gone. And then you write it on a matrix form. So here you will now have a coefficient matrix multiplied with, and here a vector, all your unknowns. My first one, that is number 2, because number 1, that was the boundary. And then 3 all the way down to Emax plus 1. So how will my coefficient matrix look like? Well, I will have minus 2 on the diagonal, of course. Then you're going to need plus 1 on the neighbors. So here should be 1, and the next one here, 1, 1, and then like that, all the way down here. 1 and 1. Then you have, for the internal points, that's not a problem, but here you have to think in terms of the boundary. So the first one we have to sort of do specially, because for this equation here, u number 1, I mean, he doesn't exist as an unknown. He belongs on this side. That's the right-hand side of the equation system. Well, if I equal to 2, then u number 1, he should be on the other side. But the first boundary, that was down here, he was 0, so that's not a problem. And for the rest of them, everything is 0. What about the last one? Well, you have Emax plus 1 as the center point. That's the one closest to the top wall. But then this guy is going to be a value different from 0. He's going to be 1. That's the boundary value. Thrown on the other side, he will be minus 1. So this is my equation system. 0 and 0, the unknown vector, and the right-hand side vector. So typically you will write this as matrix A multiplied with here my velocity vector equals the right-hand side B. And that one can be solved directly with MATLAB, not a problem at all. So let's take the time to do that. My A matrix, you have something that is called diag in MATLAB. That is a way to construct such matrices, mostly zeros, but then you have some bands alongside a diagonal or close to the diagonal. So diag, very, very easy. Should be ones. And then you will have, say, we have Emax number of unknowns, comma 1. And then we multiply that one with minus 2. I can show you if we now say Emax equals, say, 4 or something. So now the A matrix looks something like this. So the diag, he just puts minus 2 on the diagonal. That's all. But I need more than that. So A equals A. Oh, sorry, big A equals A. Then we do the same diag. And then we have ones. Sorry, ones of. But now I need one less. Now I'm going to construct the two bands next to the diagonal, and they are one shorter. So the length of the diagonal is Emax. Now I have Emax minus 1. Comma 1, like that. And then you can specify, if you look at the documentation for the diag, you can specify, is it spot on the diagonal, or is it 1 or 2 or 3 bands next to it? So if you don't say anything, like I did in the first one, you get the diagonal. Now I want 1 and 1 on each side. So you can specify that one with now minus 1. Let's do it like that. And then we take the same. But now minus 1. If I now run that one and print out the A matrix, you see I have gotten exactly what I wanted. Minus 2 on the main diagonal, plus 1 on the bands next to it. So diags, that's a convenient tool to construct these A matrices. What else do we need? Well, we're going to need the unknowns. So that one should now be just the internal unknowns, of course. So zeros of Emax comma 1. You can't use the same u that we had because he had Emax plus 2 values. He included the boundary values. Now I just want the internal points, and that's the only thing now is going to be unknowns. I need my b vector, should be the same as v, the same length, but I have one value for on the right hand side that was different from 0. He was -1. There you have it. Now I have my coefficient matrix, the unknowns, and the right hand side. So how to solve it? You can do something like this. V equals inverse of A multiplied with B. That should be the solution. Let's try that one. Hold on. Plot V, say as a red dotted line. Hold off. Then we can go back to say 100 unknowns and see if this one runs.
You have a misspell at the last plot.
Do I? Plut. Let's see how he handles that one. Undefined function, okay. Plot. Thank you. There you go. So one swoop, you get the solution. Yes, you do. But this is not the way you should do it. I mean, here you have constructed the inverse of the matrix A. You can write it like this, so you can see what's happening. Say, call him A inverse equals inv of A. And then you can multiply here with A inverse. So yeah, you find a solution, that's true. But look at the size. The matrix A, that is now 100 by 100 matrix. If you have 1,000 unknowns, he will be 1,000 by 1,000. You're going to blow the memory. But the coefficient matrix A, there we can cheat. Most of it is 0 anyway, and we just have the number, the diagonal, they are constants. They're just coefficients. So you never store the entire matrix A. So 100 by 100 matrix with mostly zeros, why should we store it? There you can cheat. A equals sparse. That's something you should be aware of. Sparse A. That is a trick. You store the matrix on a different form. You only store the values that are different from zeros. Here you have the coordinates inside the matrix, and here you have the values. Look at the size. A is sparse, but it's still 100 by 100, but he uses much less memory. The sad thing with this A inverse, that's a different story. He's a full matrix. If we print it out, A inverse, you see he has numbers different from 0 all over the place. So there you can't choose, there you can't cheat, you can't use smaller memory, the memory there. If you write whose, you see my point. A 100 by 100 requires this amount of bytes when he is sparse. When he is full, 100 by 100, you need 80 megabyte. So if you now start playing around with bigger numbers, you have 1,000 by 1,000 unknowns. And then write whose. Okay. You are getting up to very, very big numbers here very fast. But use this trick. A equals sparse. You can see the amount you save in memory using this sparse. So that's a very good trick. Never mind, that was not my point here. My point was the following. You should, if you are interested in finding the solution, never ever use inverse A. It's a very bad idea. He stores internally in memory this full matrix, and for a complex problem you're going to blow the memory. So never use him. So what should you use? You use the backslash. That one is a smart choice. He uses the same, and MATLAB uses it extremely efficient and also doesn't require much memory. So you will find there the direct solution for this matrix system sort of instantly. Very, very efficient. So use the backslash if you are seeking a direct method. Okay, any questions to that one? Okay, that was a little too much. Let's take a 10-minute break.